Today I'll be talking about resolving the diversification of Asterozoans from material mainly from Morocco and from France. And a kind of tribute to all of my French colleagues, I thought I would add a translation to the title, because most of the material is in fact here in the Université of Lyon, and a lot of my colleagues from France have very much made this possible. Now, the thing about Asterozoans is that we have a tricky relationship when it comes to the homology between these, and that has resulted in several different hypotheses on how we understand how the group evolved. So this is kind of really confounded and sort of a bit of a mystery because of the fact that we have so many different types of morphologies really appearing rapidly at the beginning of the Ordovician. So when it comes to looking at them, this kind of summarizes the kind of problem we have here. We really have today these two very sort of crown group morphologies that are very, very distinct. And the thing is, working out how these evolve from each other means we have to go deep into their ancestry. However, as with everything, it's not always as simple as that, because there are so many different morphologies out there. Now, recent phylogenomic hypotheses have concentrated on different types of relationships between the groups. In particular, whether or not the Ophiuroids, in fact, are not really related to asteroids in terms of how they're arranged, or whether or not we have this Asterozoan hypothesis where both of them have this clear relationship. Now, recent sort of phylogenomics has shown that, in fact, there is perhaps this kind of relationship that we're sort of sticking with today, showing that, in fact, these two groups diversified, and, in fact, the whole talk today really focuses on this area here. That's what happened at this moment here. But as I said, the story is not so simple, because we have these other forms, and that's what this talk is really about, is looking at these other forms like somastroids and stenoids. And my colleague Daniel Blake has been involved in this in trying to resolve and coming up with different sets of homologies to kind of resolve this issue. So the groups that we deal with within the Ordovician, they all exist within the Ordovician. Some of them are obviously extinct by the end of the Ordovician. We have the somastroids, stenoasteroids, Ophiuroids, and asteroids. And when people have tried to put them together, they found a bit of a mess. You can see here we've got a nice sort of relationship at the top here with the asteroids and the Ophiuroids. But when you go down here, you can see it's very difficult to decide where the somastroids can be placed. And stenasteroids have really come in recently and also are difficult to place where they are. So this talk is about presenting a hypothesis that allows us to sort this out and come up with a sequence of evolution within this sort of Ordovician world. Now, the way to do this is to concentrate on how the skeleton grows, and to a certain extent we've got this system where you have this sort of central umbilicral system here, and then the key thing is that we have a homology between that system of umbilicra, and then we look in more detail at how the plates are added to the system and how they develop. So to do this, I've developed a kind of little tiny sort of crude animation here, and we concentrate on these particular things here, which are these sort of Virgil series, these interconnecting series between the umbilicra in purple and this outer part. Now, the outer part has been variously interpreted as marginals and adradials and all sorts of things. And here we're showing what Blake supports and what I support, which is in fact they're part of the lateral series, and the lateral series does not occur next to the umbilicras there. So we show here that when we evolve into a stenasteroid, we just reduce this Virgil system here, but keep these adradials over here. This has made a much better case study in which to study them. Now we can start to see how the groups are diversifying. We have these groups that are developing when you're reducing this kind of Virgil series down and then developing intermediate plates to support the podal system underneath. Now, the data from this thing has come from several areas. Laurentian fauna, very well studied. The sort of Armorican fauna in Brittany. But the one we're doing today is this West Gondwana fauna, and that's where these bat stars come into play. As a very good introduction to the Fezzuata before, this has made my life very, very easy. Thanks a lot for that. So we're going to sort of skip through the Fezzuata. I don't need to say much about the fact they've got nice preservation. But in the paper that came out in the Fezzuata, that Nature paper, we have a very interesting group here, which is called the bat stars. And the bat stars themselves are interesting because although they are part of this sort of appearance of this Paleozoic or even a modern fauna, they are still remarkably basic in their form, primitive in their form almost. And in fact, it's these that can kind of unlock what's going on in the earliest Asterozoans. So going back to that previous talk, they're around that age and sort of lower part of the Tramidocian here. We have several bat stars here, but a lot of them are very poorly preserved. And the one we have that's the best here is this particular bat star here. when we focus in on them, we actually see there's a very simple system. We have a series of ambulacra, and then coming out of that, we don't have any adregular plates. We have this very nice, beautifully preserved sort of virgule plates coming out of them in a single sort of sets. The key thing here is at the end part here, we don't see any interconnecting plates here. We see a very sort of weak connection, a kind of trail of beads at the end of this system. So this is kind of being interpreted in this virgule series as being perhaps primitive. So here we have a series of those beads holding everything together. It's a development of a lateral system that we're having that therefore develops into true somasteroids and then into stasteroids as it becomes more robust and then changes. So this kind of supports this idea that we have these very sort of basal forms, Shiniasta and Vimbrasta, which also have this sort of similar system. And these ones are the Montagne Noire, and that's what I'm going to go into next. Now, Montagne Noire, to the south of us here, is an area that has some wonderful sequences of Ordovician rocks. And a lot of these are in the best places to find fossils, vineyards, and you can actually walk along and collect them here. Great field work. And it's also some asteroid world, okay? So the fact is these things are dominated by lots of asteroids, but in here there are some of the earliest examples of the asteroids and of the Ophiuroids. So within there you have the Chinian Formation, which is Tremodosian, almost the same age as the Fezuata. We can correlate them across. And then we have this later story here where we have the Landeyran Formation, where we're looking at perhaps later story. So for this part we're going to look at what's going on with this particular story. In the Chinian Formation, we have some of the earliest Proto-Ophiuroids, I'll explain those in a second, and we also have some of the earliest asteroids. The earliest Ophiuroids, Proto-Ophiuroids, are Proto-Ophiuroids because they have these additional reduced virgule series in here. Dan Blake calls these stasteroids, I don't, but that's something that we're working on at the moment. But in fact what's happening is that system has been reduced, so you actually end up with these two clades, first sort of very basal forms of Ophiuroids, and then moving up into perhaps true Paleozoic forms. So let's show this what happens on the animation. Here's a somasteroid. This is what happens. We lose that going down to the ambulacra. We gain these sort of fastigial podal plates, as they're called, and then the adradial plates. And then what I'm about to show in a minute is when these are reduced and it reduces further, we then get into what we call a kind of basal Paleozoic Ophiuroid, the one that sort of persists a bit longer. There's a thing to illustrate that there. And that's what happens next. If you move through the sequence within the Montagne Noire, we go later on into further up into Landeyran Formation. We see the evolution of the true protasterids. They lose that podial system altogether, and these are the groups that kind of persist towards the end of the Paleozoic. These ones we've used to classification using this stepped umbrellacra to classify them, but it goes all the way through to the Hunsrück slate and well on out to the Permian. And recently we found one in Western Australia going all the way to the end of the Permian. So this is the kind of morphology it's consisted, and these ones probably coexisted at the same time as a lot of the sort of, as it were, true crown group Ophiuroids. So that kind of sums up the story to a point. We start off with somasteroid, we move into Ophiuroids, Proto-Ophiuroids and into Ophiuroids, that's the morphology develops, and then we go off by reducing that system and developing these sort of marginal and supermarginal system to gain sort of modern asteroids, and that's how the whole thing works out. So where next? Well, we've done this part here down in the early part of the Ordovician, but in fact what would be great, of course, is to go to the end of the Ordovician and follow it along and see actually what happened next. How do these forms develop? And that's exactly what we're doing right now with the Taphilippota, which has an enormous diversity of protasterids like this one, and groups which are new. Perhaps they are another sort of Ophiuroid that evolved that isn't part of that protasterid clade, and perhaps is a whole new story. So that's the next part of the story, as they were, my punchline. Thank you very much.